Hello everybody, and welcome to example 3 on page 44 of the workbook. And this is our first example of a type of a work problem where we're trying to empty a tank. Okay, let's read this problem together and then we'll set it up. A cylindrical tank having a radius of 0.5 meters and a height of 2 meters is half full of kerosene, which has a density of 810 kilograms per cubic meter. We'd like to find the work needed to pump the kerosene over the top edge of the tank. Okay, so why don't we start by just labeling the dimensions that we've got here. So they tell us that the radius of this tank is 0.5, so we could write that in. And the total height is 2. Okay, and we've got a tank that's half full here. Okay, now just a word about how we want to think about this problem first. Okay, so I'd like you to picture the pump that we're using as being a pump that is floating on the top edge of our fluid. Okay, so our tank starts out as half full here, so you can imagine the pump is kind of starting out in this position. And as it pumps the fluid out, the fluid level is going to fall, and you can imagine the pump just kind of sinking so that it's floating on the surface of the kerosene at all times. Okay, well, what that means is that we're going to have the same issue that we had with the rope problems that we did earlier, and that is that different slices of the liquid are going to have to move different distances. The closer that the liquid is to the top of the tank, the less far it's going to have to move to get to the top. Okay, so we're going to use the same type of approach that we did with the rope. We're going to think of taking this liquid and to slice it into pieces. That seems kind of a strange thing to do with liquid, but we can think of it conceptually that way. So think of this as being a typical slice, okay, of our kerosene, and it's going to move a particular distance to the top of the tank, which we'll call y, just like what we did with the rope. Okay, so what we want to do then is to figure out, first of all, what is the weight of that slice that we just drew? Okay, well, to get an expression for that, think about what components might influence the weight of the slice. Okay, one thing that's definitely going to play a role is how much volume is in that slice. Okay, well, what units does volume have? Well, in our problem, meters cubed. Okay, what other factors besides the volume of the slice would influence its weight? Well, one other one that I can think of is the density. And you can see the units of the density in the problem up here, kilograms per cubic meter. Okay, so far, if you cancel units, we have kilograms overall. Okay, is kilograms a unit of weight? Not yet. Okay, what do we need to multiply? Kilograms is a unit of mass. What do we need to multiply mass by to turn it into a weight? The missing piece is acceleration of gravity. Okay, which has units of meters per second squared. Okay, and notice that if you multiply the remaining units left, kilograms times meters per second squared, we're going to get newtons, and that's a correct unit of weight. Okay, so let's see if we can fill in those pieces. Okay, starting with volume. Okay, so how do we measure the volume of the slice over here to the right? Okay, well, let me first ask you, what is the shape of that slice? If you looked at that slice from the top, what kind of a shape would you see? I'm seeing a circle there. Okay, and in fact, we know what the radius of the circle is. It's going to be the same as the radius of the tank that we see up here. So what we can do is start with the area of that circle that we're seeing. Okay, pi times the radius squared. And then to turn it into a volume, we need to take that cross-sectional area and multiply it by its thickness, its height. Okay, because that's a really thin slice, it's natural to call the height dy. So pi times 0.5 squared times dy, those three pieces together are going to give us the volume, not of the entire tank, but just of this one slice that we drew. Okay, and next we come to density. Okay, do we know what that is? Well, the problem told us that directly. It's 810 kilograms per cubic meter. And then finally, acceleration of gravity we know is 9.8. Okay, and we could do a little simplifying here. Maybe take some of these numbers and multiply them together. So if you take 0.5 squared times 810 times 9.8 and punch those into your calculator, you're going to get 1,984.5. Okay, pi, and then there's going to be a dy, and our unit should be newtons. We checked that above. Okay, so there is the weight of our slice, which represents the force. Okay, what is the other component of work besides force? It's distance. So now the question is, what is the distance that that slice travels? Okay, well, from our picture, we can see that the distance traveled is just what we're calling y. All right, so that's going to be y meters. Okay, and we are all set up. So now to get the total work, to empty that entire half tank of kerosene, we're going to add up the work of all of the individual slices, and that means doing an integral. So total work should look like the integral of the weight of our slice times the distance. So we'll put those two things in our integral. All right, and there's only one missing piece. Just as always, what about the limits of integration? Okay, now here we have to be a little bit careful. Okay, and I want to remind you of something. They told us at the beginning of the problem, this tank was not full, it was half full. That's going to have an influence on our limits here. Okay, so notice what the variable is in our integral first. It's y. Okay, so here's what we need to think about. What is the range of y values as we empty this tank? Remember what y is representing. It's the distance that a slice has to move. Okay, so what is out of all of the slices of kerosene in our tank, what is the smallest distance that a slice would have to move? Well, that would be the slice that's halfway in the middle of the tank. That's on the top. And notice that that has to move half of the height of the tank, 1 meter. Okay, so that means that the smallest value of y is going to be 1, because that top slice just has to move 1 meter. And then finally, this pump kind of sinks its way down until we finally get to the very last slice at the bottom. How far does that slice have to move to get to the top of the tank? Well, it has to move the entire 2 meters, and that tells us what our upper limit of integration is. Okay, so 1 to 2 just represents the range of different distances that those slices of kerosene need to move. Okay, and we are ready to calculate the integral, so we could maybe take this constant and move it outside, 1984.5 pi, and antiderivative of y would just be y squared over 2. Okay, and we need to evaluate that between 2 and 1. So let's see, if we substitute our two limits of integration in, we're going to get 2 squared over 2 minus 1 squared over 2. Okay, and the rest is a job for your calculator here. If you punch that in, you can double check me. I got about 9352, and whoops, 9352, and our unit should be joules because we've got newtons and meters involved in the problem. Okay, and there is our answer.